she's going to speak on two special cases of the Rational Shuffle Conjecture.
Thank you all so much for having me and for being here. Sorry about the delay. So I'd like to tell you about two special cases of the Rational Shuffle Conjecture that I proved, but in order to do that, I guess I should start with what is a shuffle conjecture, what are you talking about? So what I'm talking about are parking functions, and I'll start with the classical case, which is a little more simple, but I'm going to present them with a little twist that makes them more generalizable to the rational case. So this is a parking function. As you can see, it's a labeled path, and it stays above this main diagonal that I have there. Well, it's supposed to be yellow. And the labels are next to north steps in the path. They increase within a column. So those are all the conditions on being a parking function. There are a lot of statistics on parking functions, the most natural of which is area, which is just the number of cells between the path and the main diagonal. In this case, there are 10. The sort of next most natural to me is the word of the parking function. So traditionally, you think of the word of the parking function as a permutation of the labels, and the way you obtain that permutation is you read the diagonals from the highest diagonal, the dark blue one, to the lowest, the yellow, and within a diagonal you read from right to left. So that's why 5, 1, 8, etc. But the way to look at this statistic that's more generalizable is to imagine that I've ranked every cell of this lattice that could contain a label or a car. They're called cars because originally this is actually about parking cars on a street. So these are all the cells where I possibly could have a car, and I've ranked them in such a way that higher diagonals have higher ranks, and within a single diagonal, higher ranks are to the right. So now really when I look at the word of the parking function, I'm essentially just sorting the labels according to rank, highest rank to lowest. And then the last statistic I'm going to use here is dim, which is short for diagonal inversions. And in the classical framework, you think of this as a number of pairs of cars. The first type of pair is when the two cars are in the same diagonal. An example of this would be 3 and 6. The smaller of the two cars is on the left. And the second kind of dim is where the two cars are in adjacent diagonals, and the smaller car is on the right and in the lower diagonal. So the way that I like to think about this is that once you fix where the smaller car, I, is supposed to be, you're really looking for larger cars, J, in this sort of circular diagonal highlighted there in green. And when we highlight this on the rank table with I equals 3, which goes here in this rank 14 spot, you see that the cells I've highlighted in green are simply those whose ranks are between 14 and 23, the rank of the cell above I. That's the idea of dim I want to stick with you because that's what's going to generalize for the rational case. So why do people care about parking functions? Mainly because of the module of diagonal harmonics, at least originally. So the module of diagonal harmonics is a module of invariance, and they're invariants in two sets of variables, x1 through xn, y1 through yn, and you let Sn act on each of those sets of variables in the same way. That's what's diagonal about the action. So in 1994, Mark Heyman conjectured that the dimension of this module was n plus 1 to the n minus 1, which was pointed out to be the number of parking functions in the n by n lattice. Then later in 1994, Adriano Garcia and Mark Heyman conjectured a formula for the Frobenius characteristic of this module. And this modern phrasing of it is as nabla En, where nabla is an eigenoperator on modified Macdonald polynomials. The nabla notation was actually introduced later. It was originally this big sum of Macdonald expansion. So then in 2001 and 2002, these two conjectures were proven by Mark Heyman using algebraic geometric methods. I'm not going to get into it all. But what you'd really like once you have these two theorems, well, you know that the dimension has something to do with parking functions. You'd like the Frobenius characteristic to have something to do with parking functions. So along comes the shuffle conjecture in 2005 of Jim Hagelin, Mark Heyman, Nick Lower, Jeff Rummel, and Alexander Ulyanov, which says, this Frobenius characteristic is really a QT enumeration of parking functions using the area, dim, and word of the parking functions. So the only notation you haven't seen yet here is I have the inverse descent set, meaning the descent set of the inverse of the word. And maybe some of you can't see down here, I have the definition of the Gessel quasi-symmetrics. This is actually a quasi-symmetric expansion of what should be a symmetric function because it's a Frobenius characteristic.
So this is the inverse of the word?
IDES means sigma inverse descent set. So it's a set of descents of the inverse.
Of like permutations or?
Yeah, because the word of the parking function is a listing of the labels, and the labels are the numbers 1 through n. Okay, so this brings us to the rational side of things. So the original formulation of the rational parking functions and the rational shuffle conjecture starts with coprime sidelines. So basically I'm going to look at parking functions in a rectangle instead of in a square, and I need that m, the width, and n, the height, are coprime. And the reason for that will become apparent shortly. So again, in this rectangle now, instead of a square, I want to look at labeled paths that stay above the main diagonal, which is the line going from the bottom left to the top right corner. I've highlighted the cells it cuts through, and which has increasing labels in each column. The area is still the same because it's such a nice statistic, you can just do anything you want with it. But in order to do div and in order to do the word of the parking function, we're going to have to use that table of ranks idea that I introduced earlier. So this is the table of ranks in this case, and the formula for a rank is to, for a single cell to calculate it, you look at the bottom left corner, and if that's the point x, y, the rank of the cell is my minus nx. And because m and n are coprime, this guarantees that all the points above the main diagonal in this rectangle get different ranks. So all the cells here have different ranks. And furthermore, the rank tells you how far the cell is from the main diagonal. So this is kind of generalizing the idea of those 45-degree diagonals in the classical case. So now the word of the parking function is just simply the labels in decreasing order of ranks, like it was in the classical case. The div is more complicated. Div is always complicated. So first we're going to start off with generalizing the idea of the classical case, where if I wanted to look at what cars make divs with 2, where 2 is the smaller car in the pair, I look at the rank of 2 and the rank of the cell above it, and then I search in all of the cells whose ranks are between those. So between 6 and 11, I have 3 cells, and 2 of them are occupied with cars larger than 2. So I have a div between 2 and 5, and a div between 2 and 6. Unfortunately, these are actually temporary divs because I have to modify this still. The div is actually a temporary div plus something minus something. And instead of telling you what each of those somethings are, I'm just going to tell you a result of Angela Hicks and mine from this year about how to condense them into one thing. So when you condense these two statistics together, they basically involve the lambda of the parking function, which is an English pairs diagram found above the path. In this case, it's of the partition 3, 2, 2. Each cell of this partition has an arm and a leg, just like any partition. And when I compute this down here, that gives me the div correction for rectangles that are tall rather than wide. Essentially, the div is the temporary div minus something. And you don't really need to worry about what something is too much. But you only have to do one computation instead of 2. So those are rational parking functions. That's going to be the combinatorial side. What is going to be the symmetric function side of our new shuffle conjectures? I'm going to define that inductively. So we're going to have a family of operators, one for each pair of coprime numbers m and n. And we'll start with the base case m equals 1. So in the base case m equals 1, it turns out these operators are essentially the decay operators of that same paper from 1999 of Bergeron and Garcia. And this definition involves plopistic substitution. So if you're not familiar with plopistic substitution, the briefest introduction I can give you is that if you want to substitute some expression with variables ti into pk, you just raise each variable to the kth power. And then if you want to extend this to the entire ring of symmetric functions, you just do this additively and multiplicatively since the p lambda form a basis. So very quickly, that's the definition of the base case. And then how do we induct? Well, I'm going to take the vector mn, and I'm going to look for the closest point below it. So in this example here, m and n are 5 and 7. The closest point is here at 3, 4. And so I say that 5, 7 splits into 3, 4, and 2, 3. And I call each of those vectors a, b, and c, d, respectively. It's very straightforward to show that each of these vectors is also coprime, meaning a is coprime to b, and same for c, d. So it's valid to define QMN in terms of QAB and QCD, which is exactly what I do. I take the Lie bracket of those two operators and then just divide by a constant, and that's going to be my new operator. And the rational shuffle conjecture, which we finally got into, of Gorski and Nagut from last year, is that when you apply these, I don't know if people can see, but down here it just says QMN applied to -1 to the n. When you apply these operators to plus or minus 1, you get exactly the same kind of enumeration, but now of these rectangular parking functions, also known as rational parking functions. So this is the conjecture that I proved two cases of, the case when m and n are each, or when m is 2 or when n is 2. But before we go to that, I just want to reassure you that this is a valid extension of the shuffle conjecture. So you can kind of see tentatively that there are connections on both the symmetric and the combinatorial side, but just to pin it down, the most important thing for the symmetric function side is that you know these Q operators work well with nabla. When you conjugate by nabla, it just simply adds the second index to the first. Therefore, when I look at the case m equals n plus 1, I just get the conjugation of that d operator. And so let's look at what happens when I apply this to -1 to the n, as the conjecture would have me do. Well, nabla is a Macdonald eigenoperator, so it doesn't do anything to constants. It just flows right out. And then the d operator involves plothistic substitution. When I substitute into a constant, it doesn't do anything. So it's very easy to compute this as well and to get en. So you get nabla en. That was our old symmetric function side. Everything's copacetic. What's happening combinatorially? It's also very simple. Essentially, you just take your classical parking function and you add a column. The slope of the main diagonal changes just so slightly that everything works out. That the rank table you get has the features I wanted, that the higher diagonals have higher ranks than the lower ones, and that they're ranked from right to left within diagonals. So the areas match, the words match, and the temporary dim in the rational case matches the dim of the classical case. So all we have to do now is check that the dim correction is 0. And so now we're in the case when our rectangle is wide. So the other half of that theorem, reducing the dim correction, says when your parking function is wide, you add a certain number of cells. And this is in terms of arms and legs again. Because the legs bounded by n, it gives a really straightforward proof that you can't have any cells satisfying these inequalities. And you get everything that you want. It matches in the classical case. So, in order to move on, I have to examine the combinatorial side a little more deeply. The combinatorial side of the rational shuffle conjecture is known as a Hikita polynomial, because of a lot of work done by Hikita, proving that these are Frobenius characteristics of certain modules. Unfortunately, in the case m equals n plus 1, it's not clear that that module is isomorphic to the module of diagonal harmonics, but still, because we know they're Frobenius characteristics of something, we know that they're symmetric, for one thing. So this is the Hikita polynomial, and I'm going to need one more piece of notation, which I'm going to call rho of a set. So when I have a subset of 1 through n minus 1, I can define a composition of n just by looking at the pairwise differences. So we look at the smallest element, then the difference between the second smallest and the smallest, etc. And finally the difference between n and the largest. This will clearly be a composition of n. Notice that this does depend on which n I choose, because this could be a subset of many different 1 through n minus 1s. But when I use it, it'll be clear which n I'm referring to. So a theorem of Egor and Warrington from 2010 says that if you know your function's symmetric, but you have a quasi-symmetric expansion, you can use this composition idea to get a sure expansion. And that's what I'm going to do. I'm going to say, well, I know my polynomial is symmetric, so instead of having this Gessel, I can put this sure indexed by a composition. And I just shorten the notation here. Now, my inverse descent set of permutation of 1 through n is always going to be a subset of 1 through n minus 1. So that's why I know which n I'm talking about when I use this row notation.
Does sure of a composition mean Leven shape, or
Sorry?
what is sure of a composition mean?
You would use the determinantal formula for sure functions. Right. So now that I have this Schur expansion, I'd like to know what kind of Schur functions can occur here. So we're going to put some restrictions on these for tiny rectangles.
Wait, so sorry, for using the determinant, that's not positive, right? You have to cancel
Yeah,
that.
there'll be negative signs, possibly. So something nice is going to happen. Okay. So there's a lemma of mine that if your parking function only has cars or labels within k columns, then the parts of this composition that you get can be no bigger than k. And the reason is essentially that if you have a part of size r, that implies that in the sigma inverse, there's an increase of r cars in a row. But when you have two cars in the same column, you get a decrease. So in order to sustain this increase across r columns, I need to be able to put them in r different. In order to sustain the increase across r cars, I need to put them in r different columns. And that guarantees that r is less than or equal to k. And so since I'm going to be working with a case where there are two columns, that's one of the special cases I proved, this is very helpful, right? When there's only two columns, that means my composition can only consist of ones and twos. So the Muragan-Nakayama rule tells me how to go between Schur functions indexed by compositions and regular Schur functions. And just a little refresher, basically what you do is you take your offending long piece and you bend it down along the shape below. And this introduces a sign. You just do this iteratively until none of your pieces are sticking out too much. But if your piece is only sticking out by one, and you try to do the bend, it introduces a sign but doesn't change the shape. So you get that your Schur function with that composition is 0. So in fact, all the different compositions that could occur here are either giving me a Schur function of 0, or they're already a Schur function indexed by a partition. And the only possible partition is 2, 2, 2, 2, 2, 1, 1, 1, 1, 1. Some number of 2s, some number of 1s. So I have a huge restriction on what kind of Schur functions can occur, and I don't have any negative signs, which was a concern someone already brought up. And each of these compositions corresponds to a specific inverse descent set. Okay, so more about the combinatorics of this. How many parking functions can have each of these specified inverse descent sets? The answer is actually that there's one for every possible shape. Now, what do I mean by possible shape? I mean that every time I have a jump here of size 2, based on that lemma from the last slide, that means I'm having two cars in different columns. So for one thing, if that's going to happen r times, here, here, etc., then each column's going to need to have r possible spots. So let's look at this example. Here r is 2, I'm going to have two jumps, and I have 3 possible spots for cars in the shorter column. So I've satisfied that requirement. I'm going to show you there's exactly one filling of this shape that gives me a valid parking function here. So remember, there'll be a descent, there'll be an IDES here, when the rank of I is lower than the rank of I plus 1. So to avoid 1 being in this set, I need that 1 is ranked higher than 2. And since 1 and 2 have to go in these two spots, that forces me to put the 1 and the 2 here. Similarly with 3 and 4, the 3 has to go in the higher of the two possible spots, so I have to do this. And then every other one has to just be in order of rank, like that. So there's exactly one filling that does this. And if you did this in general, where R is giving you this IDES and R plus S is telling you how tall the second column is, you would get these statistics. It's pretty straightforward to show. So when I sum over all these possible R's and possible S's, I actually get a QT analog for each Schur function. So it's a really nice compact formula for the combinatorial side of this case of the shuffle conjecture. Hopefully I can do it for the other side if I don't run out of time. So on the other side, I had to do this inductive process where I split my operator. And so the shape I want to split is 2, 2k plus 1. The closest point is always going to be here at 1k. So these two operators are actually going to be D's. They're going to be the dk plus 1 and dk operators. And so just a reminder of what those are. Essentially, I need to compute dA, dB applied to plus or minus 1 with a and b equal to k and k plus 1 in some order, and then I'll subtract those formulas from each other and get my answer. So when I applied dB to a constant, as I talked about earlier, d applied to a constant is really straightforward because a constant with this big plothistic substitution is still just a constant. So I just have an E pop out with a sign. And then you have to be a little more subtle to get what D applied to an E is. But just following through very carefully, you get this formula and using a few tricks of plethism. And then just looking at those special cases and subtracting and just being very careful to take account of everything, I get the desired expansion in terms of QT analogs and Schur functions. So in summary, what I showed you, or what I showed you most of the proof of, is the case n equals 2 of the rational shuffle conjecture, that this symmetric function side matches this combinatorial side. In the extended abstract, I also prove the case when n equals 2. So instead of having a really skinny, long rectangle, I have a really short, long rectangle. And that's very straightforward compared to the case n equals 2. So if you wanted to go further with this, what would you do? In other words, why didn't I go further? So you probably could do this with n equals 3, just by being careful and taking account of everything. But the case n equals 3 is very much harder than the case n equals 2. And there are two main reasons for that. One is that I already pointed out it was very nice that the Murnaghan-Nakayama rule didn't give me any signs earlier. And in the case n equals 3, it will. And the other thing that was very nice is that once I specified my inverse descent set and my path, I only had one filling. That's not going to happen anymore, so you'll have a little bit of a combinatorial explosion. I think if someone did do the case m equals 3, it would be really interesting because these problems are going to occur in every higher case. And then the other possible extension would be looking at the non-coprime version. So far I've only talked about the case where the sides of my rectangle are coprime. But actually this was extended to non-coprime rectangles by myself with Francois Bergeron, Adriana Garcia, and Bo Zin this year. We didn't have this conjecture when I did this work, that's why I didn't do it. And it essentially says we can extend both the symmetric function and the combinatorial sides of these conjectures in nice ways. On the symmetric function side, we use an expansion of the EK operators and some Q operators that are defined with splitting, like the coprime ones. And on the combinatorial side, all we do is fudge the ranks a little, because if you use the normal formula for ranks, you'll get repeats. So we basically just break ties by adding an extra factor to the rank formula, and that forces ties to be broken in a way that aligns with the classical shuffle conjecture. That's all I have time for right now, unfortunately, but thank you all for listening. Are there any questions for Emily?
Have you looked a little way into the 3 case, like just to see how bad it gets, how quickly?
Not too much, because, as I said, I basically know what the pitfalls are going to be, so I'm scared of it. Anything else?
How about the non-relatively prime case?
I think that would work out nicely. This expansion wouldn't be too bad because I know the only possible common divisor when m is 2 is 2. So I only have to do one expansion of E, and then I can look at that case very specifically. And then, as I said, the ranks aren't really altered that much. So I think the combinatorial side would be very similar to what I've already done. The symmetric function side would involve a little more fudging. So I'm very optimistic that someone could do this. And actually, we have a compositional version of this as